guest speaker is Steve Pinette. And he's the Vice President of Friends of the Scarborough Marsh. And his presentation is from Volcanoes to Glaciers, the Geologic History of the Scarborough Marsh region.
I'm a retired geologist. I worked in hydrogeology, which is the study of groundwater, for years as a consultant. Prior to that, I mapped volcanic rocks off the coast of Maine for my research in graduate school. And after I retired as a geologist, I became a novelist. So I went from writing about stuff to making up stuff. Since moving to Scarborough a couple of decades ago, Scarborough Marsh has been, I've fished, I've canoed, I've even gone snorkeling in it. So it's a dear part of what I call Scarborough. So today I'd like to talk about plate tectonics. A lot of you probably heard about plate tectonics. It's kind of the continents move around on the globe. We'll talk to you about bedrock geology, the things that have, sediments, clay and silt have been deposited over the millions and billions of years, and they've solidified into rocks. We'll talk about that. We'll talk about glacial geology. There have been 11 glacial episodes in the last 2 million years, 200 million years. The last one we have a good record of that really helped shape the marsh. And then I'm going to talk to you about the post-glacial history, what happened after the glacier left, including the marsh, how the marsh was formed. I have a lot of slides. I'm going to go through this fairly quickly. But keep your questions if you want till the end. If you really need to ask, just raise your hand and take off. This is the Scarborough Marsh, as most of you know. This light blue, this is a GIS rendering of a photograph from the U.S. Fish and Wildlife Service. That's just for perspective. So we have to go way back. Talk about the geology of the Scarborough region. And the Earth was formed about 4,500 million years ago. I really don't see a whole lot of action in Scarborough until we get to about 530 million years ago. So there's a lot going on. Right about here is when those of us who used iron in our lives, which is all of us, this is about the time that the banded iron deposits where we get most of our iron ore came from. This is when the Earth's atmosphere, about 2 billion years ago, was when the Earth's atmosphere started producing excess oxygen. There's a lot happened that has been recorded in what we refer to as the Canadian Shield from this period here. But in Scarborough, we probably started seeing the effects in about around 450 million years ago. So the period I'll be talking about is from about here to here. This is when the continent that had North America on it collided with another continent, or separated from another continent. And this is kind of the proto-Atlantic Ocean hiatus. Those continents eventually came together around 300 million years ago, and they formed the continent of megacontinent of Pangaea. And then around this time, 220 million years ago, North America and South America, Africa separated. And we have a record of that in Scarborough as well. And then we skip a whole bunch of time, and we had 11 separate glacial events in this last couple million years, only one of which we have a record of in Scarborough. I'm just giving you this for reference. You don't have to memorize any of this. So the geology is based on, I'm going to talk about it, it's based on plate tectonics. These plates are moving around. As they're moving around, their rock is being eroded and it's being deposited in the ocean. There's volcanic rocks that are being generated. We use South America as an example. So in South America, the whole Peru, Chile coast, what they call the Peru-Chile Trench, you have the Pacific plate moving under South America, And as it's going down, the sediments are being heated. They're coming up as magma and forming the Andes mountain volcanoes. That went on off the coast of what is now Maine at some point, several times actually. In the middle of these oceans, the Pacific Ocean, the Atlantic Ocean, you have the plates are moving apart. Like Iceland's sitting on the mid-Atlantic bridge right there. That's, I mean, farther up toward the north. So plates are being consumed and plates are being made. This is sort of a cross-section showing what's going on in South America, right there. As these water-rich sediments are heated, they produce a magma generally in this. This would be what they call andesite or rhyolite. You know, there's a range of magmas, and this is what goes on at the Mid-Atlantic Ridge. So back about 750 million years ago, this is what they theorized the continents looked like. They were kind of scattered about. These areas are mountain ranges that they've been able to trace from this period. I don't know what the red dots are. I got the slide from somebody, I can't remember what the red dots are. But this was the arrangement. We're looking at it from the equator right now. So this is about 550 million years ago. For those of you who know about geologic time scales, it's in the Cambrian era. And things to note, Laurentia is where North America is. It's the plate that North America is riding on for many million years, 500 more million years. Baltica is Western Europe and the Scandinavian countries. So note that in this rendering, they're essentially going in different directions. But a little over 130 million years afterward, Laurentia, North America and Baltica are together. You get this megacontinent of Gondwana that's eventually going to move toward North America. You have this little Avalonia, this representation here is what we call a microcontinent. That's eventually going to collide with North America. And the reason this is important is because that's where all our rocks that we have on the coast now were generated. This is a poor resolution shot, but this is essentially a fragment of Gondwana land. It's moving toward North America, and in between, you're eroding sediment, you're eroding rock, and you're depositing it into the ocean. And same with ancestral North America. You've got the Iapetus Ocean in between, and so about 430 million years ago, in what we call a Silurian era, you had this mass that was eroding sediments. They're coming into this ocean basin, and the Elliott Formation, which I'll show you later on a map, that's where it's being deposited. It's been deposited. It's being buried by the Kittery Formation, which is another formation that we see in Scarborough. The Cushing Volcanics, which you see in Prout's Neck, they're being generated here. You have they're either being generated from this slab that's subducting or this slab that's subducting. And you have the Falmouth Brunswick volcanic sequence down in the 295 area. So this is the last slide I'm going to show you. About 330 million years ago, all the continents in America or on the globe came together. So this is called the Pangea. You'll hear some people say reunite Pangea or reunite Gondwana land. That's what they're referring to. So the USA is right there. This is and Canada. South America is here. The US and South America, the North America and South America aren't going to be connected for a while. This is Africa, and you can, I can read it better than I can. So, actually, it's not the last slide. 200 million years ago, this massive continent now starts spreading apart. and it's spread apart for the last 200 million years until we get what we have today. So in cross-section, about 420 million years ago, this is a vertical section, just a cartoon. You have Apollonia, or a fragment of Gondwana land that's coming toward North America. A little later, you have the Proto-African plate, Gondwana land, coming to North America. They collide in around 320 million years old. They keep pushing against one another, and eventually they've created about as much elevation as they can, and then erosion starts. And eventually, about 50 more million years, they start spreading apart. And the important thing about erosion is in southwestern Maine, they figured that about 15 kilometers of rock have been eroded over the last 200 million years. So there's a lot of the rock record that we're not seeing because it's been eroded. You have some of the rock record that's a little more recent in Canada and in the central United States and southeastern United States, but northern New England's, we go up till about 400 million years old. So if you look at a generalized map of a geologic map of the Appalachians, you have oceanic crust, which is it's basalt. It's dark, it's black to dark gray. You have the coastal volcanic belt, which is probably in the vicinity of 400 million years old, and that was associated with Avalon, that little microcontinent that crashed into North America. The rocks that we have pertain to Scarborough Bay, Scarborough Marsh area are these Cambrian Ordovician volcanic rocks. Since this was produced in 2002, they've actually been redated. They're not Cambrian, which is 500 to 507 million years old. They're Ordovician, which is in the 450 million year old category. So you have oceanic crust here, and this gray is the original Laurasia, original North America in Canada. That's in Canada. The other thing to note is when we go from northern Maine, we have essentially the rocks look like they did when they were deposited. They're hard, they've been indurated, but they haven't been changed a lot. As you move to southern Maine, the mineralogy's changed. When you heat a shale and a siltstone, a sandstone, when you heat them and put them under pressure, the mineralogy changes. And so the theory is that as you go further south, you're looking at a deeper part of the Earth's crust. The rocks that were 15 kilometers or more deep are now at the surface. And we know this because the minerals that we see here in these rocks are minerals that would be stable at burial depths of 15 kilometers and temperatures about 500 to 700 degrees, thereabouts. It varies depending on where you are. So these rocks, when the mountains were built, these rocks were in the roots of the mountains, not in the upper parts. Whereas in northern Maine, we're probably looking at the upper part of the mountain system. So in cross section again, this is you've got what they call composite Avalon, which is actually Gondwana land. You've got the sediments in medial New England. You've got continental, the original North American continent. So how does this relate to Scarborough? This is part of Arthur Hussey's map of the area. Arthur Hussey is the late Arthur Hussey is a professor former professor from Bowdoin College. He's mapped from Kittery to up the Kittery to Penobscot Bay, and he's responsible for the maps in this area. So the Elliott Formation I showed you, mentioned a while ago, that's this one, and it's also here. The things to note here is this color is what they call the Scarborough Formation. this, the Proud's Neck, you've got the Cushing Formation, and I forget what this one is. But anyway, these are faults right here. So not only were these folded during the mountain building process, imagine taking the two sides of a rock and pushing them together, you're gonna get all these waves, mountains, you know, troughs and valleys. So you've done that, and in addition, you've broken it up, so you have, this is the South Portland Fault, this is, I forget what it is, I can't read from here. Anyway, you've got, just looking at this, you got 4 faults, actually 5 with this called the Johns Fault. So a closer look, you've got the Scarborough Formation, which I'll show you pictures of. It doesn't have a lot of, it doesn't outcrop a lot. You've got the, this is the Diamond Island Formation. It's a really rusty black rock. Once you see it, once I show you pictures of it, you'll know you've seen it before. So, looking at further down the marsh toward the coast, this is Proud's Neck. You've got the Cape Elizabeth Formation, which I'll show you pictures of. You've got the Cushing Formation, which is a volcanic unit. It's made up of volcanic rocks. And you've got another unit, which is part of the Cushing Formation, which is also volcanic. You've got the Scarborough Formation, the Jewel Formation. They're all local names. You get the Sperwink Formation. Sperwink is volcanic or another volcanic rock. You've got a limestone somewhere. Anyway, this, if you were to look at all these rocks and outcrop, you know, on any given day without having samples to compare, you might not be able to tell the difference. They're, you know, a lot of them are pretty similar. So if you were to look at a vertical slice through these rocks, and you can see how folded they are, you get the various faults. These are all inactive faults, by the way. They haven't been active for, you know, 400 million years, most of them. So this is the Elliott Formation, that kind of violet color. It was originally a siltstone or claystone that was metamorphosed. It was buried and then pressurized and heated. This is the Scarborough Formation. It's not pretty. It's black, dark gray. It's rusty. Sometimes it kind of has a bluish sheen to it. This is Scarborough Formation. That was the Scarborough Formation on Winnick's Hill. And this is on Higgins Beach. This is the Spring Point Formation, which is volcanic rock. Folds in the Spring Point Formation. As these rocks were being pushed together, there were big folds, and then this obviously is a smaller fold. The geologists, you look at these. These are all the things I'm going to mention are all things that people have, geologists have noted. You know, pretty much with field observation and a microscope. You know, there's some things that require a little more lab work, but most of this mapping has been done just by a guy in the field. So this is the contact between the Spring Point Formation, which is a volcanic rock, and the Scarborough Formation, which is that ugly blackish gray rock. And the Scarborough Formation is above the Spring Point Formation. So you had volcanic activity, and then you had a quiet period, and you deposited clay and silt and a little sandstone. This is a Sperwink limestone. It's the only limestone in the area. Limestone is usually deposited in a lagoon where you have quiet water, not a whole lot of circular, isolated lagoons, so you have calcium carbonate in the ocean and precipitate. The Jewel Formation. Jewel Formation and the Diamond Island Formation, I think, are almost the same. So the Diamond Island Formation, they're equal age, they look a lot different, but they're, Jewel Island Formation looks a lot like the Scarborough Formation. It's black, it's rusty. People who have wells in this formation on the islands, they're very sulfide rich, so you smell the rotten egg smell. And this was probably deposited in a deep basin, deep ocean basin where there was no circulation, there was very little oxygen. And that's why it gets the rusty color. This is an outcrop on Old Orchard Beach. This is a Kilry Formation. If it wasn't crusted like that, you'd see light bands alternating with dark bands. Light bands are sandstone. The light bands are silt shale. Found this right in the front yard of the Black Point Fire Station. It's supposed to be the limestone from the Scarborough Formation. I didn't have one way to tell if it's limestone is you have hydrochloric acid, put a little drop on it, if it fizzes, it's limestone. I didn't have one with me, so I couldn't tell, but that's what it's mapped as. So the Cushing Formation, it's the oldest rock that we have in this area. It was a volcano. It's dated, they dated around 450 plus or minus million years, maybe a little older. So this was ash. You remember Mount St. Helens? The ash from that, rhyolite ash. Mineralogically and chemically, it's kind of like a granite, the composition of a granite, except it's a lot finer grain. So these layers are the original deposition layers, the ash. We don't know if it was deposited through air or through water. It probably was deposited through air first, and whether it was settled in the water and became a sediment, we don't know, or I don't know. So Garrison Cove, this is where the old fort was in the late 1600s. I forget the Indian's name. Was it Montague? Yeah, they were trying to undercut the fort. So this is not far from where I imagine that is. This is from the east side of Proud's Neck. This is the Cushing Formation from another vantage point, but the Cushing Formation is folded. So right here, these layers are horizontal, but you could go up the cliff walk and you'll see some of the beds are vertical. So it varies quite a bit. This is all folded. Cape Elizabeth Formation. It's probably the most pervasive formation we have right along the shoreline. It's it's not a great picture. I should have taken a head-on picture, but it looks silvery. It has a lot of white mica in it. So if you look at a flat surface, we call it cleavage surface, it looks silvery, and it has these little buggers that kind of these little protrusions. They're these little bumps throughout. They're called garnets, the mineral garnet. So it's kind of a brownish mineral, and that indicates its metamorphic grade, or how the temperatures and pressures that it was subjected to when it was buried. So those garnets are real key for a geologist to determine how deep they were buried. Folds within the Cape Elizabeth Formation. We also have this rock. I told you that we had a record of when the continent split about 200 million years ago. What we call these dikes, D-I-K-E-S, and these are basalt, the rock from the upper mantle, and as the continents were spreading apart, they fractured, and wherever they fractured, you got basalt like this up and down the eastern seaboard. So if you're walking along and you see these rocks, it's what we call a basalt dike, and you'll see they're usually hexagonal prisms and oriented almost flat, and they result when you intrude a hot magma against a cold rock. It solidifies very quickly, and it kind of shrinks, and you get these hexagonal prisms. So anyway, it's a lot of people use them as steps. If they're vertical, people use them as steps into the mainland. So, like I said, This is when, in the Triassic, 200 million years ago, when ancestral North America separated from Gondwanaland. That's when we got these dikes. So whenever you see these dikes, they're about 200 million years old. So we're here right now, and we don't have a record. We don't have any record of the rock sequence up until almost the end of our geologic history. So we've eroded like a Setuago, almost 15 kilometers of rock. We have rock record elsewhere, so we know something was going on, but we don't have it in New England, or especially in Maine. So there were 11 glaciations, but we only have a record of one in Maine. And the maximum extent of the ice shelf was, it went beyond George's Bank. So a cross section kind of showing you what happened. It was actually grounded on George's Bank. It couldn't move anymore. And on George's Bank, it was calving us into the ocean. About 1,600 years ago, the ocean was right up to the glacier. About 1,000 years later, the glacier temperature was getting warmer. Glacier was starting to melt, and move back. It was receding. Glacier doesn't really move back; it just melts in place, so it looks like it's moving back. But it moves forward, but it doesn't move back. It just looks like it. And so you've probably seen, if you've lived in Maine, this area of Maine for a while, you've probably seen this clay that we have all around in stream beds. Dig a foundation. Sometimes you encounter it. Sometimes if you dig deep enough, they call it blue snot. It's real soft. It's called the Presumpscot Formation. And while the glacier was receding, there was the land hadn't rebounded yet, but the glacier was melting, and so all the water that was in the glacier is now melting, so it causes sea level rise. So for a period, let's say around 14,000 years ago, glacier was back here, sea level was right at the snout of the glacier, and it was depositing rock flowers, rock fragments that had ground up to clay size, silt size. It was depositing that into these valleys and off the coast. So these valleys, up until this is about Millinocket, they're full of this blue clay. And that's why we know how far the glacier, or where the glacier was at what time, because they can date the fossils in these. We also know, because we had the find in Scarborough that about 10,500 years ago, we had a woolly mammoth. It was found on Wally Fengler's property in 1959. They dated it as 10,500 years ago. Prior to that, they thought it might have been an elephant that had, from some circus that had gone wild. But when they dated it, they realized they dated the tusk and or the teeth, I can't remember which. They realized it was a woolly mammoth. There were woolly mammoth, there were sea lions, there were other Arctic type critters that were off the coast of Maine. So 14,000 years ago, we have the glacier is receding, it's melting, sea level is rising. So you have, this is current sea level. You have sea level that's about, in this area, about a maximum of 75 feet above current sea level. So you've got a lot of, you're depositing this Presumpscot Formation into a water body. So this fine clay is being deposited. Right at the glacial margin, you're depositing fine sand and gravels. Not unlike what you see in gravel pits today, because most of our gravel pits that we have were at the glacier margin. The glacier was spewing out sand and gravel. It was deposited close to the glacier, and the Presumpscot clay was being deposited farther out. So sea level rose. Let me go back. Sea level rose, and then as the glacier receded, the continent, which had been depressed by the weight of the glaciers, now rebounds. It's like an ice cube, but it'll float back up really slowly. So if you try to put an ice cube underwater and let it, it'll pop out. Well, the continent was essentially doing that. So for a period, Maine was, this is current sea level. The water level is about 65 feet or more, depending on what part of the coast you're on, below current sea level. So you had beach environment down, further off the coast, at greater depth. During that period, the rivers and streams that were discharging onto the coast were cutting valleys, stream valleys and river valleys. So you have these, they call it shelf valleys. At one point, everything was in equilibrium and the water started to rise. And so we have Crescent Beach was isolated. Crescent Beach was a barrier beach. Scarborough Beach. We have the beginning of marsh formation. It's said that once you get a barrier beach, and the Scarborough Marsh was kind of an open ocean for a while. But once you got a barrier beach and you got enough silt behind it, right nowadays they theorize that if you have about 10 feet of silt, you can grow eelgrass. Once you start growing eelgrass and you start trapping sand and silt, that's when your salt marsh starts to accumulate. So we're starting to, pretty close to current sea level. We're seeing beach and marsh formation, barrier islands, and so on. Just another graphic to show you, at this point, wherever you have a low stand shoreline, it cuts a profile into the rock and into the sediments. So I'm sure if you were to dive down there, you'd see beach features, cobbles, and what you see around the coast of Maine right now. And when the glacier, when the seawater was at its highest, as it came down, it also eroded benches, what we call beach benches. So especially in the Augusta area, there are all these beach benches that are cut, old ancient shorelines that are now high above sea level, but they were cut into the countryside. So this is a geologic map of Maine. The green stuff is what we call glacial till. That's kind of a mixture of clay, silt, mud, boulders, cobbles, and it's it's like pulling a bulldozer over the countryside, and whatever it comes up with, that's what the glacier was doing. Kind of a fuzzy photo of what glacial till looks like. You have large fragments, you get small fragments, you get clay, silt fragments. This is from a sand pit in West Scarborough. This is just kind of a medium to fine sand that you will find on some beaches. Sometimes it'll have ripples. This ripple shows the direction of the water is moving in this direction. Usually the steeper sides on the downflow side. This is one good exposure for the Presumpscot Formation. It's the upper part of it is dry. It's very dense clay. The lower part of it is this is where it's wet, it's gray. If you get down below the water table, it becomes that snotty clay, which you can't really cite anything on. This is the same, a different location, the Presumpscot clay, and the light. These light portions are these little sand laminae that are in there. It was depositing clay, and depending on what the glacier was putting out, it might, if there was more water coming out, say during a spring melt, it was powerful enough to move sand. In it, there can also be shell fragments. They dated these shell fragments, so they know the relative ages of these. So Scarborough, this color, the PP, the violet color is the Presumpscot, that clay formation. Anywhere you see this dark rose color, that's sand, usually deposited near the glacier by a stream or at the mouth of the stream. These are these right here, these greenish things. are what they call moraines. They're at the very snout of the glacier. As the glacier is moving forward, imagine the bulldozer as it's moving that pile of rubble. That's ultimately, wherever it stops, that ultimately is going to be that moraine. So they, by tying these moraines together, they were, the ice margin was here at various times as it was moving either forward or backward. This is just sand, sand from around the river, this is the Nonsuch River, sand, wetland deposits. Only glacial till in this one. Okay, moving on further south. This gray is bedrock. This is Blue Hill. A lot of rock in here. Old Scarborough Marsh is mapped as salt marsh deposit. You get some glacial till in here. That was deposited. Usually glacial till is deposited at high elevation around mountains. These are more recent deposits, the beach deposits, West Beach, Old Orchard, Pine Point. Scratch. These are what they call glacial striations. As the glacier was moving over rock, it had cobbles in the bottom, and depending on the hardness of the cobbles, if they were granite, for example, they could scratch the rock that was underneath. If it was shale, it would be ground into the fragment would be ground up, and that's what becomes your clay silt. So back to the orient you to the marsh. The person who did most work, even until now, was a fellow by the name of Stuart Farrell. He's a graduate of UMass at Amherst, and so he worked in the Scarborough region, and he was a coastal geologist, but he also had a lot of interest in Scarborough Marsh. He ran these transects up and down the Libby River, the Jones Creek, the Dunstan, Scarborough River, the Nonsuch River, and he cored through the marsh. And I'm only going to show you one of his cross sections, which I've done a poor job coloring. But so this is that Presumpscot. No, this is the sand. Keep in mind that, or remember this sand, because it'll be important later. So you had sand, then you had it's sand, silt, clay. You had organic, peat here. Then you had the marsh peat. The water depth must have been sufficient. The conditions were right. The Goldilocks conditions, so that you could deposit peat. The water wasn't too rapid. There were enough nutrients coming in. But note it's supposed to be a salt marsh peat, but note that we're getting a wetland peat here, a freshwater wetland peat. That's in the Jones Creek area, and I think part of the reason for that is because that area is now tidal flow beyond Pine Point Road up to Jones Creek is restricted enough so that we're no longer getting a salt marsh environment, we're getting a freshwater environment, and that should change at some point. So back in 1940, somebody took an aerial photo from a plane, I guess, and the reason I'm showing you this is there used to be a river outlet in here called the Little River, and it used to flow. I forget what. There's a major, I don't know if it's a condo unit or there's a major building there now. Around 1875, the outlet was blocked when they constructed the railroad. There wasn't enough flushing in there, and so sediment, instead of going in, was being deposited there. And so now, what used to be it used to get water from here and water from here. The Jones Creek is now kind of isolated. It's part of the problem that we're facing right now. This is Stuart Farrell's work again, and his area took this from the plane. There are two things I'm going to show you about this. This is Pine Point, and this is what we call an ebb tide delta. When the ebb tide when the tide is coming out of the marsh, it's depositing sand in this. And this is a delta. Imagine a Mississippi River delta, except it's on a much smaller scale. And this is supposed to be the flood tide delta. I mislabeled it. So as the water's coming into the marsh, it's taking sand from the beach and wherever, and it's depositing it behind. In Scarborough, the Scarborough Marsh deposits more as the tide is coming in than as the tide is coming out. So we're getting more sediment coming in, more sand and stuff coming into the marsh, but it's not going up into the marsh. It's kind of being deposited locally. You know, is it Turner's Bar? Is that this area?
Yeah.
So we're getting more sediment coming in than is going out, which is a good thing. But we're not getting it up to beyond the railroad and the Eastern Trail and the culverts. So all this sediment that should be replenishing the marsh is kind of staying a little farther south. I'm just going to show you these slides that kind of illustrate. I'm going to wrap it up fairly quickly. So, kind of illustrate that the Turner's Bar, Turner's Flats, whatever it's called, there's a lot of sand movement there. Somebody, Farrell did some calculations and he estimated about 2,700 cubic yards of sand moves back and forth during the course of a year in there. It may not all go up river, it may not all go down, but it's moving around. And this is, imagine you're on Black Rock and you're looking toward Pine Point. This is the Nonesuch River coming in. This is kind of the broader Scarborough River. Just to illustrate, this is one shot where he put a stake in, and this is, you know, the next tidal cycle. The sand wave has moved farther down. Again, in one tidal cycle, it's moved to here. Here, this stake was here, and 2 tidal cycles, it's moved, I think it was 19 feet. And these are large sand waves. If you go into the sand flats and where they're steep and you look, you'll see these sand waves after the tide goes out, and they're generally formed under high velocities where the water's really gushing around those narrow passages, and it creates. These are about some are, I think he said they were 25 feet long and about a foot high. The smaller ones are regular low velocity flow. So where does Old Orchard Beach and the Scarborough River get its sand from? From the waves crashing onto the shore. But what direction are they most prevalent in? It seems that we're getting most of our sand from southeasterly winds. Summer winds coming off the Bermuda High seem to be providing a lot of our sand. This is a wave refraction model that Farrell did. We also get winds from the northeast, and he did a model for that, but we don't get the spacing of these lines is supposed to be indicative of the velocity, and note that we're not getting the velocity in Old Orchard, Scarborough, Pine Point area. It's very, very low. We're not, these are intense northeasterly storms, but we're not getting a lot of sediment impacting our beach, and we're not getting a lot of erosion impacting our beach. Kind of a rose diagram that shows you, these are orientations of our dominant wind directions, and the percent is the percentage of time. We're getting northeasterly winds probably more frequently than we're getting these various orientations, but they're not contributing a whole lot of material. The other important reason for this slide is we get coarse sand up until about this point, and from here on in, we have the fine sand that you'll find in the Scarborough Marsh and Pine Point Beach and West Beach and so on. And the reason for that appears to be the wind direction, where these winds they're coming right in. This is where the biggest wave forces are hitting the beach, and so they can transport larger sand fraction. You know, the velocity of the water is what determines what size material can be transported. Heavy currents can transport all types of material, but low velocity currents can only transport things like fine sand, clay, and silt. Kind of the same slide, I'm showing you what the bottom topography looks like. You have the nearshore ramp, that fine beach sand, or that fine to medium beach sand. You have a shelf valley. This is where some discharge eroded the valley in the material. You have rocky zones near, this is Wood Island, Bluff Island, Rocky Zone. You have another shelf valley, the Scarborough River, probably carved that one out at some point. Another shelf valley where the Sperling comes in. I don't know what's causing this one, what to do with that one. But I'm sure that if you've ever lobstered, you probably know where all these are. So the kind of the most exciting thing for me was, as I was putting the thing together, there's evidence to suggest that the Saco River actually used to empty in Scarborough Marsh. And Shelf Valley would have emptied in this Shelf Valley right here. And this looks from Proud's Neck to Wood Island, so it's almost a north-south orientation. And this is probably where the old Saco River ran through. And this is unproven, but the theory is that at some point the Saco River was running through Scarborough. At some point it got plugged up, the channel got plugged up with till or glacial till or something, and then it reoriented itself to its current track. So if you look at the current Saco River, this is kind of it. And right around here, you have, this is an unsuch river. Map version, this is the current. You still see the depressions that would have channeled it. So what problems? That's kind of the geology or the geologic history of Scarborough Marsh as it is, without getting into the plants and all else. But there's some things that are going to challenge the marsh's existence, and one of them is sea level rise. Right now, these are the sea level rise rates for coastal Maine up until I think about 2006, 2009. So sea level's rising about 1.8 millimeters per year, and the marshes, the salt marshes in southern New England are only accreting, or they're only being constructed at about 1 millimeter a year. So their sea level's rising much more quickly than the marshes are rising. So at some point, we may not have a marsh. We may have something different. And to illustrate this is from the Maine Geologic Survey. This is kind of using projections on sea level rise. This is the marshes that exist today. The light green is the high marsh. If you cross the marsh today, that's probably the area that was flooded when you came in. The tide was almost high. It was, I don't know if it was spring tide, but it was quite high. So on spring tide, the area that's flooded corresponds to that, the dark green and the light green. The area that floods on, say, an 8-foot tide is the dark green. So if you raise the sea level 3.3 feet, that low marsh, that dark area increases, and the high marsh spreads out everywhere. Focus on Pine Point. There's some other areas, maybe here. Note what happens when you raise it little over 3 feet. So it starts moving up on Pine Point and Winnick's Neck also. If you raise it 6 feet, which is one of the projections for sea level rise in the next 100 years, you lose a lot of Pine Point. You start losing significant parts of Winnick's Neck, and a lot of the marsh becomes open water. Now, that's if the marsh doesn't accrete, doesn't build itself up. If it builds itself up at the same rate as sea level rise, you know, this is going to be a different scenario. You'll probably get the same footprint of the marsh, but the marsh will be able to keep up, so you might not get this open water. But in order for it to do that, you need to have sediment that actually makes it into the upper marsh, which isn't happening much beyond, there's not a whole lot of sediment that's moving beyond the Eastern Trail up in there, or the Libby River marsh. That's not getting a whole lot of sediment. So what's at risk? Well, some properties are at risk, obviously. This is the salt marsh sparrow. It's traditionally, well, not traditionally, it puts its nest is usually centimeters off the marsh surface, or the high water surface. Well, and they adjust that, I'm sure, year to year, and you know, they build a nest and they know the conditions. But what's going to happen with more sea level rise and more storms, we're going to get storm surges that are probably going to wipe out these nests. So these birds are endangered. They're in Scarborough Marsh right now as we speak. The other thing that's threatening the marsh right now, and sea level rise may solve this, is Phragmites. It's that nice tall plant that everybody would like to have in a vase or in a pot somewhere. And this is in the Libby River Marsh, and I mean, it's probably 12 feet tall. And what it does is it takes over a marsh very quickly, and as it propagates, it builds the marsh, it elevates the marsh surface, which would be a good thing if we wanted to keep up with sea level rise. But once it overtakes the marsh, all the plants, none of the plants can live, and the animals, the birds and other animals don't use it. So it's not it's an invasive, what we call an invasive. And Friends of Scarborough Marsh paid a consultant to map the extent of Phragmites, and it usually it thrives at 20 seawater salinities, 20 parts per million. So existing seawater is 30 parts per million. In marsh, with each tidal flushing, it stays about 30 parts per million as it goes up into the marsh. That's like 30 marbles and 30 parts per thousand, actually. 30 salt marbles and 1,000 water marbles. But Phragmites comes in when that decreases to about 20 parts per thousand. Where does that happen? Where there's a stormwater runoff, a lot of stormwater runoff. Like if you look where the Tractor Supply store is, right opposite the parking lot, you have a lot of stormwater runoff there. Probably you have some upstream of Route 1. The DOT's culverts are an improvement over what they used to be, but there's still not enough salt water getting up in there. Those are the major areas, but I'll show you a slide. This is a slide I just threw in. I sent this to the Portland Water District. Portland Water District, I was doing some work in here. This is the downstream side of the Black Point Road in the Libby River Marsh. This is fresh water. There's a water main that comes through here and goes under, and the water main has a break in it, and so it must have been going on for a while. So these Phragmites, like I said, they grow in brackish conditions. So although there are no Phragmites anywhere on this side of the Libby River Marsh, they're all upstream because of the salt water mixing with the fresh water that's coming out of here. You've got a nice long line of Phragmites. So the study that we had Norman Dove Associates do a study for us. They used a combination of aerial imagery and walking the field, and they mapped Phragmites. Phragmites cover, the marsh is about 3,000 acres. The saltwater marsh is 3,000 acres. Phragmites covers about 132 acres of it. It's not as bad as we thought, but the major areas are up in the Libby River Marsh, upstream of the Black Point Road, and again in what we call the Dunstan Marsh, which is upstream of Route 1. And all these numbers correspond to other colonies. There's some along the Nonsuch River as well. I haven't seen this one. So you've got little isolated occurrences everywhere. These are obviously the major ones we have to tackle. And that's all I have.
Thank you.